Hi everyone, my name is Stephanie Parker, and as I did in my course project proposal, this course project will be on machine learning for predicting customer satisfaction at U.S. airlines. So, customer experience is crucial in the airline industry because understanding passenger satisfaction helps airlines improve service quality. U.S. airlines have made various strides in improving the quality of airline travel for their customers over the last decade. However, surveys and reports indicate that passengers are still looking for more. In my research, I had found that U.S. airlines are leaving as much as 1.4 billion on average in annual revenue on the table by not making improvements to their customer experience. So the question is, how can airline industries predict and improve customer experience? Of course, a growing solution is to use machine learning because through the use of machine learning, we can analyze historical and real time airline data to predict customer satisfaction by finding patterns and relationship in the data that humans may, of course, miss. And we can find that using data such as the patterns in service and delays, demographics, and reviews, things like that. So this will allow airlines to take the right step towards enhancing their customer experience, boosting their loyalty, increasing their revenue long term, which will in the end help them to meet and increase customer satisfaction. So the goal of this project is to predict customer satisfaction using data that classifies passenger satisfaction as either satisfied or neutral and dissatisfied based on various customer experience features like delays, service quality, seat comfort, things like that. For this project, the target variable is customer satisfaction. This is defined as a discrete value, like I mentioned earlier. So this would be a binary classification. The experience will evaluate two models or two machine learning methods, the SVM and the gradient boosting machine learning methods, to predict the airline customer satisfaction. The models will use supervised learning because the data set included will include labels for the customer satisfaction. These experiments are based on another report whose results indicated that although SVM did show overfitting and perform less in generalization and testing, SVM was the better model since it did outperform in accuracy and F1 score. My hypothesis, though, is that gradient boosting will outperform SVM in accuracy and the F1 score since it is better for handling more flexible, or it's more flexible for handling more text values and numeric values as opposed to SVM, which is better at handling more numeric values. So the original source dataset contains U.S. airline passenger satisfaction surveys that were recorded back in 2015 from a website called Kaggle. The dataset is fairly large with over 100,000 observations and with more than 20 variables or factors that characterize the passenger experience and the service aspects of the airline. These include things like customer type, age, class, in-flight Wi-Fi service, things like that. And then based off these experiences, the survey will provide the target variable, which is customer satisfaction, as a binary value of satisfied or neutral and dissatisfied. So the goal, of course, of this project is to predict airline customer service satisfaction using machine learning, the models that I mentioned before, the SVM model and the gradient boosting model. However, I realized that another key aspect of predicting customer satisfaction is also explaining what drives customer satisfaction. So what I did was based off the featured metrics that or features that were in the data set, I created engineered metrics, which are going to be used to summarize and kind of simplify those original features that were in the original data set. So when I do my feature importance analysis, if I see specific features that are in the top, I can categorize those into a major set that will help me to explain what is driving it and not just give me the point that A, Y, and Z is what those features are. So for my engineered features, I have total delay, which is going to be of course, the total flight delay, and that accounts for two of the features in the data set. I have the service quality, which I split into average service rating and then the total service score. And as you can see, that has the majority of the data set features like seat comfort and online boarding, gate location, things like that. Things that are a service or service quality based metrics. Then I have a loyalty indicator. And this is going to be like a binary indicator for the customer type. There is a customer type and then a travel type that is part of this one. And then I have the long flight, which is going to also account for the distance of the flight for anything that's greater than 1,000 miles. And then I have delay category, which there's a length, a total delay that is actually the engineered feature within this one, and based off the length of time, it's either classified as short, moderate, or no if it's within a certain amount of length. So at the end, when I do my feature importance, when I look at the top 10 scores, this will help me to determine what is basically driving customer satisfaction, instead of just helping me to know what is those specific features. Like, what can I classify those features into to make more sense of why these are the top features. So next, I will talk about implementation. I'll talk about the training and the test data sets, the baseline dummy model that I use. Then I'll talk about implementation of the SVM model and then the gradient boosting model. So in my code, the training and test data sets are split using skitlearn's train test split function. This it kept the ratio of the target variable, which is customer satisfaction, satisfied or neutral and dissatisfied, the same in both sets. And then I used a random seed to make it reproducible every time that the model ran. So 20% of the data was used as the test set, and then 80% of the data was used for the training set. The SVM model did use a smaller subset of training to make the computational time a lot faster, and then I'll talk about that a little bit more in a later slide. So a baseline or the dummy model was used to provide kind of a reference points for the SVM, the gradient boosting models. So what it did was, if basically it provided a F1 score, and what I did was compare the F1 score of the dummy model to the SVM and the gradient boosting models. If my F1 score of the SVM and the gradient boosting models was less than my dummy model, that indicated there was a problem with my implementation. If it was better, if it was or greater than the F1 score for the dummy model, that means that my implementation was correct. So basically, I just compared the models just to make sure that the correctness of the metrics that I was provided was correct, and that the implementation of my models was also correct. So to implement the dummy model, I used a dummy classifier, which is a baseline model in skitlearn that doesn't learn from the data itself in a complex way. It made predictions using a simple rule. So I used the rule most frequent strategy, which made the model always predict the class that occurred the most in the training set. So for example, if 70% of the passengers are unsatisfied in the data set, then it will always predict unsatisfied. So basically, I used it to prove that the models, the SVM, the gradient models, were learning. They're learning the patterns from the features rather than just guessing the majority class. For implementation for the SVM model, the first thing that I do want to mention is that I had originally trained the SVM model with the entire data set, which was, as I mentioned, over 100,000 rows of data. But this was extremely inefficient. The model took hours upon hours to run. I think it was like over 8 hours to run. And I was looking to improve the time to make it a lot faster. So since it took several hours and it was extremely low, to make the model faster, the SVM model had to be trained using a smaller subset of the data, which was about 5% of the training data. But to make sure that it was a fair comparison to the gradient model, the SVM model was evaluated on the full test set, which was 20%, as I mentioned before. So the first thing in implementation was defining that subset of data, which I had just said, then doing the pre-processing. There were some missing values in the data set that I had to account for. So for the SVM model, any missing numeric values were replaced with a median value of those column values, and then they were scaled. And then any text values were replaced with the most frequent value. And then after pre-processing that data, I did a pipeline where the SVC probability was set to true so that the probability scores for each prediction could have been calculated. And then after training the model, the predictions are made on the full test set and the result metrics are computed. So then the SVM model does not provide any type of feature importance. So I had to use permutation importance to measure how each feature affected the model's predictions. I also use feature or permutation importance for gradient model as well. From that point, the top features are printed, and then the plot, a bar chart is plotted with those top features. So for implementation of the gradient boosting model, I do some pre-processing, again, because there are some missing values in the data set. I use a column transformer named preproc XGB, which assigns any missing value with the median value so that it can be used. Then we do some pre-processing in the pipeline that uses a histogram-based algorithm, and also does an evaluation of the metrics for any binary classification. Then I use a function to find the best hyperparameter using a threefold cross-validation. Once the best hyperparameters are found, then the model is trained on the full training data, and then predictions are made on the test set. So then once that training is done, the model's features importance are calculated using the permutation importance, like I mentioned in the previous slide, just to measure how each feature affects the model's predictions. And then the top features are printed and then plotted as a bar chart again. So finally, we'll talk about the results of the models. I'll first talk about the metrics analysis, and then we'll talk about feature importance analysis. For metric analysis, the table produced below was from the code that I produced. It shows that the F1 scores for the SVM and gradient boosting models are higher than the dummy model. F1 score, which confirms to me that implementation of the models is correct, and I can depend on these metrics that are coming out of it. One thing that's interesting is that F1 score, the 0.7 or 7074, actually shows that 70% of that data set is showing satisfied passengers, which means that the data set is a little class imbalanced. It's not evenly balanced between satisfied and unsatisfied, which is interesting to note. But for the SVM model, which was trained for only 5% of the training data, it was able to still achieve a pretty high performance. The precision and the recall of the SVM model are balanced. They show like the model detects satisfied passengers efficiently. The gradient boosting model did outperform the SVM model, but it only did it slightly. This could possibly be because it uses the full training data set instead of a subset that the SVM model uses, but regardless, the gradient boosting model did show a higher F1 score, a higher precision, and a higher recall, which shows that overall the gradient boosting model had the best performance out of the SVM model. So for the top 10 features for the SVM model, the most influential metrics for predicting customer satisfaction are determined to be seat comfort, in-flight entertainment, and food and drink. For the top 10 features for the gradient boosting model, the most influential metrics for predicting customer satisfaction are determined to be seat comfort, in-flight entertainment, and then the travel and customer type. So based off these, identify top matrix between both models we can conclude that the passenger experience is what drives satisfaction. So this will include seat comfort, departure, arrival time, food and drinks, gate location, things like that were included in the engineered metrics for service that I had shown earlier. So in conclusion, by using machine learning algorithms to predict customer satisfaction, we're able to evaluate the SVM and the gradient boosting model to learn more and to predict airline customer satisfaction. So based off the results, the SVM and gradient boosting methods were able to both achieve a pretty high F1 score, which indicates that they can both accurately predict airline customer satisfaction. However, based off my hypothesis, which was proven to be true, gradient boosting did outperform the SVM model. The feature importance analysis did reveal that focusing on like service-based factors like seat comfort and in-flight entertainment, things like that, had the highest impact on the overall customer satisfaction. This is showing that service quality-based metrics are what drives customer satisfaction, which kind of makes sense in a way because what people are really saying that when they want more is that they just want quality service. And the majority of the factors and the data set were service-based factors. If you remember back to the slide where I engineered those metrics, a good majority of everything that was in there was service-based metrics. So basically, to me, this kind of makes sense because in a situation where I'm having a delay in my flight, or what really would drive my satisfaction is, yes, I'm upset that the flight is delayed, but what's going to make me more upset that the flight is delayed or my level of comfort and the quality of the customer service while I am being delayed? Both are important, but at the end of the day, I would remember more how I'm treated and how things were done customer service wise than the flight being delayed. So this makes sense. It does make sense that demographics would be a little bit less important. It's more just about how you're being treated, the customer service, the quality of the customer service that would drive customer satisfaction. So that's actually pretty interesting and pretty cool to see. Here is my references. I thank you guys for watching. I hope you have a great day.